Good afternoon. Welcome to our second lecture for this day. I have some introduction here for Deep. So Deep is currently working towards his PhD in the Department of Computer Science at the University of California, Irvine. He received his Master in Computer Science from University of California also in 2019, and bachelor degree in Computer Science and Engineering from Jadavpur, University, India in 2015. His research interests include self-aware embedded systems, memory systems, and hyperscale data center systems. His PhD research has been supported by multiple awards from German Academic Exchange Services, National Science Foundation, and private industry, more specifically Meta, right? So thank you for joining us, Deep. I know that you had a long trip from California to here. So please, you can give your talk for us now.
Thank you. I'm very honored to be here. This is one of my first presentations, broader audience, and I'm very glad I could be here in person because I know virtual talks are not that fun. So I really appreciate the opportunity, and I thank all the CASS members to invite me and help me with presenting my research. But there is a small problem. I know it's just after lunch. We had a heavy meal. Second problem, I'm speaking English, which I'm sure is not super fun. Third is I'm going to stay a little bit up towards the stack in the hierarchy of the memory, right? So I need your help. So if there are any parts which seem like you cannot follow, please feel free to interrupt me so that I can help answer the questions as we go along. It's slightly long talk, so at any point if you think things are not like you can follow along with me, so I'll be happy to take questions along the way. Okay, so before I start talking about my research, I'll just quickly introduce myself first. So I usually go by my nickname, which is Deep. I am from the eastern part of India, from a small city called Calcutta. So you can see it here on the map. And we are also very famous for our sweets. So I was in Pelotas visiting for the last 3 days. So I felt like I'm in home again because in my country, not every state is famous for its sweets, but Calcutta is. So when I was there, I was just having non-stop sugar diet for 3 days. So I'm right now on a sugar high, but it's going down. So I am also in my final year of PhD, which means there's one more person I need to convince, my advisor, before I can graduate. So my advisor is Nikhil Dutt. He is also working in the area of embedded systems, EDA, and he has been guiding me for the last 5 years. I'm also a part-time student researcher at Meta. I'm part of their capacity engineering and analysis team. So basically, the team is planning how much hardware they require. I have a little bit of insights into how these things work, so I'll present that in the second part of the slides. But for the most part, I think today we'll be talking about my a broader vision of what I'm working on with one specific use case which is very kind of related to the community here, approximate memories. And then towards the second half, I'll go slightly above in these layers of abstraction. So if you can see in this figure, I'm showing 5 layers of abstraction, starting from the device technology layer, which I think a lot of people here are experts on. Then if you go slightly higher, then we have the architecture layer, where we are looking at the CPUs, GPUs, accelerators, and so on. Then you have the operating systems or kernel layer. Then you have vendor libraries. For example, if you're using NVIDIA GPUs, then you have CUDA. And then at the end, a topmost layer, you have the applications themselves. Maybe you are using PyTorch for writing these applications and so on. So across all these layers, there are like numerous researchers working, particularly with a focus in memory, which is my area. And the key problem that lies is memory continues to be a bottleneck no matter which layer you look at. Right? So I will not go into the device layer, but I'll give you some examples of my work in some of these upper layers of the stack. So starting with architecture, then I'll have a few works in the operating systems layer, and then just to show you a sneak peek what we are doing in the application. Okay. So the challenges that I will address today in this talk is how do we manage memory resources at runtime. So if you have a system that you are not able to modify and you need to run your applications given a correct existing design, how do you manage the memory resources across the different layers in the stack in the most recent generation of embedded hardware, and goals in mind. So in some cases, you might have energy efficiency as the goal. In some cases, you might have higher performance as the goal. So depending on a few use cases that we look into, the goals can change. And we will see how, from a memory point of view, we can address these different goals. And one of the key parts that differentiates my work from, we'll see the state of the art, is I'm looking at the end-to-end stack. So we have, if you're running 3 or 4 applications in the system, then I consider the emergent behavior with all these different applications together that forms the pipeline. And then I also look at systems at scale. So if you have not one machine, but if you have to configure these hundreds of machines at runtime, so these are the two differentiating factors which makes some of these challenges even harder to solve. And in order to solve these challenges, there are 2 techniques that I'll describe. First is how can we use computational self-awareness principles? I haven't talked about that yet, but I'll go over it briefly in a few moments. And then the second part, which is very interesting for us, is how do we exploit approximation in solving these challenges. Okay. So this is an overview of the talk today. I'll start with what do we mean by computational self-awareness. So for the longest time in the EDA community, we have been designing systems by extensively studying the application that we have at hand, and then coming up with architectures or device layer solutions that optimizes whatever goal we have. So for example, if I'm trying to make a Gaussian filter, I try to see what is the best way to construct that circuit, given like I have this much power budget, right? So that has been a way of kind of making these circuits. And but on the other hand, if we look at humans, like when we are young, we try to learn our surrounding environments, and we try to learn how to kind of by ourselves, we try to observe what's going on in the system, what's going on in the environment, and we learn how to kind of adapt to those changes, right? For example, if you imagine there's a kid and there's a hot iron to which presses your clothes, when the kid doesn't know that the iron is hot when the mother is, let's say, ironing the clothes, then if the kid touches it, it'll suddenly feel that there's a hot burn and then withdraw his hand suddenly, right? So, but the next time, the kid will remember, oh, last time when I had touched that hot iron, I got a super heat on my fingers and I pulled my hand back. And so whenever the next time when he sees that iron, the kid will remember that this is not a good experience that I had last time, and so I should not be touching these hot irons. So that's just an example of how one kid would learn in this case. And we try to kind of think about how we can deploy some of these ideas into computer systems as well, right? And so when we talk about self-awareness, you'll see there are lots of communities working on making systems self-aware. And so if you ask a person whose research is in artificial intelligence, they'll say, oh, it's a software solution to create neural networks and try to adapt the computer systems. If you ask someone from control theory, they'll say, oh, if we can do a system identification and then maybe have a PID controller to control the system. Similarly, if you ask someone who's doing totally neuroscience, they will have a different answer. So we first need to define what does self-awareness mean in our context, right? In this case, computer systems. So we pick one definition from 2015. This Kuhn's paper is very popular. This was published in a dark stool conference. So basically in Germany, a group of researchers started drinking beers in the evening, and they thought, okay, how do we define self-awareness for computer systems? And they said, here are the 2 primary requirements. First is, let's say we have the system here, and then within the system, there is also another mirror. Think of it that there's a reflective mirror here, where the system knows that, okay, there is another entity, and it can learn models about itself and the environment that it is operating under. right? So this is a simple model of the system that's there. And this model is constantly updating. So if the system is undergoing, let's say, a temperature rise, the model kind of understands, okay, this is what is happening when the temperature has risen due to some reason external. Right? So that's the first requirement of having a reflection of the system. The second is, once you have this mirror, you can use that mirror to reason about different things without actually executing them, right? So for example, if I have certain tasks running on, let's say, the big cores in the ARM heterogeneous processors, then if I have a model of the heterogeneous processor at the back of my hand, I can have some reasoning about, let's say, what happens if I move the tasks to the little cores. So if I have a model of the system, I can ask the model questions without actually running experiments. Right? It may not be accurate. It may be an estimate. But using these estimates, we can actually continuously keep adapting these models. Right? So the two requirements that we define for self-awareness in computer systems are, first, that there will be some models, abstract notion of models, that will capture knowledge on an ongoing basis about the system and the environment. And secondly, we will use that model in a way so that we can reason about different actuations with whatever goals that we have. And all of this can change at runtime. Right? So your goals can change, the system's behavior may change, your environment that you're operating under circumstances, those may change. Okay? So that's the broad overview. And then we'll take more concrete examples and see how this actually works. But before I dive into that, we should understand what self-awareness is not, right? So it's not tied to any one particular area of research. So you can think of, like, if you ask the artificial intelligence community, it's not just a neural network to solve all these problems, but we will see, like, it has a lot of different properties, and depending on what use case you are looking at, we might have to tease out these different properties. Okay? You may solve some of these problems using different areas of research, but one research area, for example, will not define all the properties of self-awareness. Okay. So let's go back to the abstraction layers, and then we will see how a very simple self-aware system would look like. So here we have, again, these 5 layers that I'm going to refer back in my slides again and again. And let's add some stuff in it to do some more fun. Okay, so we start having some sensors on the right. So on the right, I think the text is not very clear, but it's just the application layer with sensors. So sensors in the application layer, sensors in the library layer, and so on. Some of these can be virtual sensors. For example, what is the quality of service? Some of them can be a physical sensor. For example, what's the current temperature, what's the current power, and so on. And then on the left-hand side, we have the different actuators at that level. So an example actuator at the application layer could be your resolution. So depending on what's the current goal, you might switch to different video resolutions at runtime. Similarly, an application, a kernel layer actuator might be how do you map the tasks to different cores? If you have hundreds of cores and 5 single-thread processes, where do you want to run them? And so on. So you have all these sensors and actuators. And if you have just this system with no connection of the actuators to the sensors, there is a lot of potential that we could exploit, but right now we are not doing anything with it. If we add a loop, let's say if we close this sensor actuator loop with some smartness here. So for example, we have a manager, and that manager is aware of what goals we have, and the manager can observe using the sensors in all the layers what's going on. And given whatever goal the user has set, the manager has some intelligence. Like, let's say it can be a heuristic, it can be a simple algorithm, it can be a neural network model. But the manager, looking at the current goal and whatever sensors it can observe from, will decide what the actuator values are. Right? So this is a very classic ODA loop, which stands for observe, decide, and act loop. And this system can reason about, like, for example, okay, my last change of moving the task from small core to big core had a very high increase in temperature, so those kind of small stuff it can perform. but it is still not self-aware because we don't meet the two criteria yet. To make it self-aware, we will add another small element in this design. So if we have this system here, we will add another model of the system that I am showing here as the reflection component and use that model during the management decisions, right? So at runtime, using all the information that we have from the system and the environment, we are continuously updating this model here. And then the manager can query the model and ask questions to kind of decide what the actuations are going to be. So this is a very simple instance of how computational self-awareness would look like in a high level, at a like high level 5-layer hierarchy of the memory. Right? So we will now use this kind of a blueprint to solve one or two use cases. Particularly in our case, there'll be some approximation that we will kind of look into. Okay. Any questions so far? Is the pace good or should I slow down? All good? Okay. All right, so now let's start talking a little bit more concrete about memory. Now, memory research has been going on for decades, right? And there are, you can see like at different layers of the abstraction, memory might mean different things to different people. So at the lowest layer, people will talk about memory cells, milled up using some transistors. Then at the architecture level, researchers would talk about registers, cache memory, scratchpad memory, high bandwidth memory for GPUs, and so on. At the operating system layer, the abstractions are heap, stack, memory pages. And at the application layer, we're looking at data structures, right? And at all these levels of abstraction, we have had tons and tons of works that researchers have done, both for approximations and memory management policies, right? So for approximations, like these are just some examples, but these, what the gist of this is, if you look at the works that we are showing here, usually they are focusing on one particular layer in the memory abstraction, right? So if people are working with approximations of DRAM, then the papers are all about DRAM, right? Changing the refresh rates and so on. If you're looking at cache memories, then they are looking at SRAM, then it's changing the voltage levels of the SRAM. So what we are trying to do is look at it more holistically. So if you have a memory hierarchy, then what happens if you want to coordinate all of these different layers of abstractions? So that's the general context. And then we also want these things to happen using self-awareness principles. So we don't want manual tuning. So we don't want developers or system designers to go in and study the system to choose the correct values of approximation. So we want this, the system to automatically learn what's best for it. And similarly, like if you look at the memory management policies, a lot of it kind of expectation is on the application developer. So if you are writing a CUDA kernel, you expect that the engineer who's writing these applications are very well versed with how the GPU architecture is, and they know how the memory patterns are, and they can write very efficient code. But what if that's not the case, right? So we want the life of programmers to be as easy as possible, while we can take most of the optimizations burden away from them, right? So that's the context here. And just to summarize, yeah, so we have a new architectures, we have new applications, and these across the memory stack, we need new techniques to solve all of these problems. And this is just like the overview of the 3 sections of today's talk. So first part, we'll go a little bit deeper into approximation, and then we'll look at some newer systems where we actually can't change the architecture, but we will look at very recent state-of-the-art data center hardware and see what's going on there, how we can deploy self-awareness principles there. And last but not the very least, we'll look a very quick glance into one of the most recent applications where there's a lot of investor money, which is self-driving cars. And we'll see what are the memory challenges that's there and how can self-awareness work. So we'll start with the first one, which is memory management with a deeper dive into approximation. So The goal here is there are certain applications that are running, and we want to meet the quality requirements of that application. Now, it can be a machine learning application where the quality metric is accuracy. It can be a image processing application where the quality metric is, let's say, PSNR, and so on. And that's the primary requirement. So we'll specify that we need to maintain a certain level of accuracy. And then the secondary requirement is consume the least amount of energy. So those are the two conditions that we have for this particular use case. And then we can sense whatever we want from all these different layers. We can change these layers. And then the goal is we'll kind of develop this memory manager as we go along. So there are tons of works that our group has done in different layers of the stack. But for this talk, at least for the architecture layer, I'll focus on one or two papers. So I think folks here are very familiar with circuits. So I won't go into too much recap, but this is just how a memory hierarchy typically looks like in a system. So you have the registers, which are very close to the CPU cores, and you can access them very fast. But the problem is you only have a limited number of registers. So let's say EAX, EBX, and so on in x86. The names might be different in different architectures, but nevertheless, like let's say you have a 4K video, they're never going to fit in the registers that you have. So the solution to that is, okay, why don't we add a little bit slower memory, which costs a little bit less, maybe in terms of dollars or in terms of area. And then you have this hierarchy where registers are faster than cache, cache is faster than main memory faster than flash disk. And the trade-off is you have more cycles, but you can have larger and larger as you go down the hierarchy. Right? So what if you want to approximate, let's say, one or two of these layers? So there has been a lot of research from the devices side where researchers have looked into the trade-offs of what happens if, let's say, you relax the accuracy requirement a little. So let's say I write 5 in my main memory, and I'm okay to read slightly different numbers sometimes. Let's say I write 5, I'm okay to read 4.99. So that's the general idea. And the way to do it is very dependent on what technology you are using under the hood. So for example, in cache, if you're using SRAMs, this is an example model which kind of shows for a 90 nanometer device technology how the SRAM would behave. So ideally, if you don't want any errors, let's say you want to operate at 1 volts, let's say, and then if you start scaling down the VDD on the left, so you 0.7, 0.6, and so on, you observe on the Y that there are certain bit flips, right? And on the Y, we are showing the bit error rate as we scale down the VDD on the X. And this behavior is different for reads and writes. So when you're reading SRAMs, then you follow the blue line. And if you're writing the SRAM, then you follow the red line. Okay? So, but this model is just for the SRAM caches for 90 nanometer device type. If you look into DRAM, the hardware again is different. So in this case, it's no longer the operating voltage, but it's the refresh rates. So here on the x-axis, we have the DRAM refresh rate. So for example, ideally you want to refresh, let's say for DDR4 every 64 milliseconds. But let's say you kind of relax that and you are okay to have a little bit of bit flips in certain banks of the DRAM. And then you kind of scale down the refresh rate slowly. So instead of refreshing every 64 milliseconds, let's say you refresh every 1 second, every 5 seconds, every 20 seconds on the x-axis. And with that, you have different trade-offs. So as you kind of refresh less and less, you start observing more and more errors in the memory, right? And so here we are showing the in red how the error rate would look like, and this is the axis for that. And then this is how much power you'd save. You're doing all of this to gain something, right? And in this case, that's power for us. So in both of these cases, the idea is you have some hardware knobs that you can tune, and that will expose different bit error rate and power characteristics. Okay? Questions so far? So how does this manifest in the application at hand? This is just a simple example before we dive into the actual solution. So this is an example where I'm performing a very simple clustering, k-means clustering on this image. And you can see these are, if we don't have any approximation, these are the clusters that get formed. And then if, let's say, I had approximations, and here I am approximating 3 layers of the memory hierarchy. So I have L1 cache, L2 cache, and main memory. And I have, instead of operating them at the recommended voltage, I have, or refresh rates, I have scaled it down. So let's say I have, instead of 1.7, instead of 1 for L2, I have 0.7. And instead of refreshing every 64 milliseconds, I'm refreshing every 20 seconds. So that leads to not the exact image that we were expecting, right? So now you can see there's some grains formed. But let's say like I'm okay with a certain amount of grains in the output. So that's the assumption. So for every application, you kind of expect that you can be okay with a little amount of QoS that you can sacrifice. So if we can do that, then my task is given a certain constraint. So let's say I give you, you can only have, let's say, 5 pixels that are different from this picture. Then can we find out what's the maximum power that we can save by configuring these 3 correctly? So that's what we are going to solve. So in terms of memory approximation, so now the simplest problem would be to start with 1 layer. So let's say we only look at L1 cache, we only look at L2 cache. But I think what's more interesting is now, let's say we have this 3-layer hierarchy, and we want to find out what's the optimal knob configuration for this L1, L2, and DRAM. Okay? So that's the part that we will cover today. So we can look at very simple examples first. So if you have a static knob, then that would mean just enabling or disabling approximation. As you make it more complicated, you'll have different types of memory technologies kind of interacting with each other. And another problem here is if you have, let's say, an L1 cache, L2 cache, and main memory, you have very different memory access patterns, because let's say you have a fault in L2, and if you're reading from DRAM, those might propagate up or down depending on if you're reading or writing, right? So it's not very predictable what the effects are when you go beyond this 1 layer of zoning into 1 layer. So what we are designing is this intelligent cross-layer controller that looks into this hierarchy, and given a quality output, decides what these levels should be, right? So this might be voltage for SRAM, it might be refresh rate for DRAM, for STT-MRAM it can be read-write current, so on. And we will use this computational self-awareness to solve this now. So this is another graphic to kind of help explain what the challenges are and why we can't solve it using a static optimization problem. So on this figure, we'll take two layers in the hierarchy. So this is L1 and this is L2. And let's say these are the operating voltages for each of these layers for one application. So if you operate both of them at 1 volts, then we don't expect any errors because they are operating at the vendor recommended setting. So there are no errors here. But as you start scaling down the voltages on either layers, then you start seeing larger and larger errors, which are denoted with the radius of the circles. Right? We'll make it slightly more complicated. So now we'll add power on top. So once you start scaling down the voltage, you start saving power. So which means, like, if you look at this chart, the greener you are, the less power that you consume. So if you don't care about quality at all, then probably it's better to run at this operating point because this is the most energy efficient, right? But now let's say I have another constraint on top. I'm saying the radius cannot exceed a certain limit. So let's say I add this another circle, which is kind of restricting how much errors I can tolerate. And this is a very simple example. So you write 100 numbers in the array and read, and then you are calculating how many numbers have bit flips. And then that's kind of dictating the radius. So if you add this bound, then you can see now within this bound, these are all the circles, operating points that lie within this bound. But if I have the second metric, which is power, then this is probably my best operating point, right? Because I am within the bound and this has the less power. This is just for one application, right? And now what happens if we look at other applications or other inputs? So this is just, instead of looking at one application, we now add another application, application B, where you can see these optimal points are changing. This is the same application B with a different input. So this is, let's say, a video stream, and this is a secondary video stream. You can see in all these three cases, the operating points are completely different, right? So we want to understand what's these operating points, ideal operating points, but we don't know what the system looks like. We don't know how it's reacting to different environments, and that's what we're going to solve next. So if you are interested in what's the exact memory technology and how these knobs operate, this is a quick overview of that. But the key takeaway from this slide is no matter which kind of technology you choose, you'll find one or more knobs to tune. Right? In this work, we'll focus on just two of them, so operating voltage for SRAM and refresh rates for DRAM in the slides. But if you have these models, then you can play around with anything that you want. Okay, so now how do we solve this? So firstly, it's hard to actually come up with these new chips which will have these knobs. So what we'll do is we'll emulate the behavior of these faults. And to do that, we have two options. So we can run everything in Gem5 and kind of add these models within Gem5. But if you want to run these, let's say, machine learning applications or even video processing applications on Gem5, you know how long it's going to take, right? So what we did is we took the hardware approach, which is the harder approach. So we have an open source RISC-V processor, and we took that as our starting point. And given that the ISA is open source, we modified the CPU's architecture a little bit. And we added different components inside the memory hierarchy to emulate these behaviors, to see what would happen if the L1 was operating at 0.7 instead of 0.1. And then overall, we'll see how this works. So first is we took a Xilinx FPGA and we synthesized the core, and then we modified in the memory hierarchy. So you have the cache controller here, the main memory controller here, and then within that, we added some fault injectors. And depending on which memory technology model you are choosing, you can control the bit error rates in the memory hierarchy. And this is like very representative of how the data would flow when you make these reads and writes, right? So if you have faults in the DRAM, it will propagate to L2. If you write some errors in the L1, it will propagate to L2 when you kind of when there's a cache miss, right? So this is a very realistic way to emulate this hierarchy while kind of enabling us to explore different technologies. Now to control the approximations, there are some new assembly instructions that we added. For example, approximation enable, disable, what's the L1 level, L2 approximation level, and so on. And then like to exploit this new ISA instructions, we have some kernel modules so that at the highest level, the C application or whatever language you're using don't need to change assemblies. But these kernel modules kind of can choose which models you're exploring. And also, you can have, instead of malloc, there is a approx malloc function call. And whenever you allocate memory from the heap using approx malloc, it knows that it's okay to allocate these regions where you can tolerate faults. Because if you're running an operating system, you don't want the operating system to suddenly experience bit flips. That will crash the entire machine, right? So this allows us to only approximate the regions in memory which are processing high amounts of data where you can tolerate these faults. Videos, for example, are very, very good examples for that. Images, videos, machine learning data sets, those are all like approx malloc can be applied. Okay. Now, everything is happening inside this small box, which is the Seams controller. Right? So here, now we will do a deeper dive into what's going on in between. To solve the problem, so what we need to do is we need to understand how the system and environment reacts to to different settings of this L1, L2, and main memory, right? So to solve this problem, what we use it will be some variant of a reinforcement learning technique. What we will, but there are some assumptions. We don't know how the system dynamics are, so we don't know like which setting causes what in the final output of the application, and we assume that these can continuously change. So the effects on, let's say, canny edge detector may be completely different from k-means, and we want this to be able to adapt at runtime and yet find the new operating points. And the exact way to do this, what we are doing here, is we have this small table which has a little bit of information about what's the current states. So what's your setting for L1, what's your setting for L2, what's your setting for DRAM, and then with that, how is the system reacting to the environment with some sort of rewards. And you have given a current state, what's the best action that you can take, right? And this table is continuously adapting to whatever it is observing. And initially, we don't know anything about the system. So there is a policy initialization period where you kind of start exploring. There can be a lot of different ways to solve that. So for example, you can have a pre-populated table, but in our case, we assume we start from scratch. And then we kind of keep adapting it based on what the current applications are running. There are a lot of ways to solve this. The way we are using is called temporal difference learning. So it's another variant of Q-learning where you keep updating these tables, but you also keep a little bit of history in the form of some traces. So you know how each action in the previous units of time impacted the system. So that's called eligibility traces, and you combine this Q-learning table with the eligibility traces to make this converge a lot faster than like traditional Q-learning systems. So while in this work we are using Q-learning, it's not that reinforcement learning is just solving all of self-awareness problems. This is just one particular solution for the case that we are looking at, which is optimizing without knowing the design points ahead of time. So I'll quickly go over the results. So in this case, what we want is, the first case is the easy case, where let's say all you care about is energy, right? And your goal is over time, your policy, which is kind of what the memory manager is executing, is able to reduce the power over time. Initially, you can imagine when the policy is starting, it doesn't even understand that 0.7 is going to lead to the lowest energy, right? So that needs the memory manager needs to learn that. And so this is kind of the experiment that does that. So on the x-axis, we are running, so first of all, we are running an image processing application. And on the x-axis is the frames that are being processed. And on the y-axis, you have the amount of power that you're consuming, right? And if you are operating at the highest level of configuration, you consume 100, and then slowly as you tone it down, then the memory power goes down. Right? And so first is like a smaller configuration space. So we limit the number of knobs that we have. And this is just showing, okay, our method works. And eventually it figures out if this is the minimum power consumption, it can eventually go there and can kind of converge, right, after some time. As the states increase, so if you, instead of having 64 knob configurations, if you have now 700 knob configurations, you can see like it still converges. It takes a lot longer. For example, in this case, you can see almost after 20, you have a near optimal solution. In this case, it's almost after 100. And when the configuration space increases, that's when you can see the advantage of TD lambda. So TD lambda, just compared to Q-learning, keeps the history of using the eligibility traces. So because of this history, we are able to converge much faster than the blue line here. So orange is the TD lambda, and blue is the Q-learning line. Right? So now we'll make it more interesting. So now in this picture, we don't have any any quality constraints, right? So our only goal is learn how to reduce the memory power, and that's fairly easy to learn. Now what we will add are some constraints, right? Quality constraints. So the application that we are looking at is canny edge detector, and the inputs are a video. The QoS metric is root mean square error, and our goal is given a quality constraint, we want to stay within that constraint as much as we can, and on top of that, minimize power. And our state-of-the-art comparison is Dart, which you can imagine is kind of looking at the all possible knobs at design time using one application. And then given that application, it decides, okay, this is going to be the best configuration, and runs with that knob configuration throughout. Right? So in the first part, where both Dart and in this case Seams has seen what the application looks like given the QoS constraint, and they both can kind of perform equally well. On the y-axis, this is the quality, and on the bottom one, this is memory power. So both of them are kind of equal here. But what we'll do next is we will add an unknown video completely and change these inputs right here. Okay, so this is a new scene. No one has seen this before. And suddenly you can see Dart starts missing the quality constraint, right? It shoots up and stays above the QoS constraint line. The power doesn't change, but remember, like for us, the primary constraint was actually staying under this black dashed line. Right? So here you can see Seams is trying to find what's the best configuration to stay within this black dash, and that's what it can find within this short time period here, right? Whereas Dart keeps on violating that. And then eventually here, there's another new scene after 60. That's when Seams can again kind of understand, hey, there's another new scene, and it's exploring what's the best knob configuration, and here it's exploring again, right? So this is just one simple example like of how Seams is self-optimizing, trying to find what's the best configuration knobs by using the TD lambda process that I described earlier. Another interesting results here, so let's move ahead a bit, is let's assume now you have somehow filled the table and Seams knows how to meet one particular constraint. But now there is a situation where you have different amounts of constraints. So initially you start with a constraint of 10 here, then you change the constraint to 85, then you change it back to 30, right? So this is another different problem which requires coordination among these knobs of L1, L2, and main memory. So the optimal configuration here will not be the same as this part, not be the same as this part. And of course, with that, the power will also change. But here we can see that's what like Seams can self-optimize and figure out, okay, this is probably the configuration that can stay in this region. Then it will switch to a new configuration here, switch to another configuration here. And with that, you have powers also changing dynamically. Now, what is the exact configuration that we can do a deep dive? It'll be hard for me to explain why this is happening. And sometimes that's the hard part, which self-optimizing is actually doing for us. But these are the exact values that it took to kind of achieve these numbers here, right? So overall, I think there are two main takeaways. So we could coordinate between all of these L1, L2, and main memory, figure out how these dynamic access patterns kind of interact with each other, and eventually achieve the goal that we wanted, which was maintaining the dynamic QoS constraints while minimizing the power. So that's kind of the summary of the first part of the talk, right? So any questions so far before we move along? All right, so that's, I think, a lot about approximations till now. So next is we'll switch gears a little bit and we'll move one layer above the stack to the operating systems layer, right? And in order to do this, I think I'll kind of change gears a bit and look at what one of the systems that represents the modern data center environment. So imagine, let's say now we have explored some architectural techniques, and now I give you a system where you cannot modify anything. So you cannot change the voltage of L1, L2, you cannot change anything. So in that case, what can we do from memory management side, right? So this is an example of what, right now, before I show you the exact hardware, let me quickly introduce the challenges in memory in these newer technologies. So let's say I have a system which has a CPU, which has a GPU, which has an accelerator. And these are kind of, you can think of one of the most recent embedded systems, which has like these SoCs with all different kinds of compute units. And with new compute units, memory still faces new kinds of challenges, right? So for example, if you have a many core CPU, let's say 100 core CPU, the performance of these different cores, what's going to happen to the application layer is very dynamic. It's very unpredictable. Um, for a single core, it's already hard to model. And as you scale it up, it's very hard. For GPUs, for example, when you have a shared memory that you are kind of sharing between the CPU and the GPU cores, there is a lot of memory contention that happens. And although there are high bandwidth memories which are emerging to solve these problems, you still have a lot of contention that creates a lot of memory pressure, right? And for accelerators, it's the same story. So before, let's say you have designed a coprocessor for neural networks, and then you want to accelerate a part of your program. But in order to initiate the acceleration process, you need to provide the accelerator with some data. And so before you start the process of acceleration, you need to move some data from the CPU to the accelerator's unit. And then when the computation is done, you move the data back. So no matter what architecture you look at, you'll still be seeing lots of new types of problems with memory. And understanding like the telemetry from memory is even harder as you move on the right-hand side. So for CPU, you might have certain counters, but for GPUs, some of these counters are hidden. Accelerators, it's a open like world. No, there's no counters, especially memory counters for accelerators at all. So now, given this kind of an environment, I'll talk about one use case for us, which is through what happened to Facebook. So during COVID, normally what Facebook does is, so if you have a requirement of capacity, so let's say suddenly people start using Instagram more, then the solution is just buy more servers and add it to the data centers. But the problem happened when COVID struck. So during COVID, there were two problems. Firstly, people were staying at home. So there was a lot of more interactions from users. So the demands for all these different services went up. But on the other hand, there was a supply chain disruption. So the typical problem where you throw money at it, buy more servers, couldn't work because you cannot get these servers in time, right? So that's when what they wanted to do is with the existing set of servers, how can you optimize to get the most work done using whatever techniques you can? And thanks to that, like our research is still funded. So what we will do is we will take a look at one of the existing state-of-the-art architectures that they're using for compute type workloads. So they have different types of hardware, and these are all open source hardware. So the designs, you can go to opencompute.org, and all the designs of PCBs, motherboards, everything is open source. This is one particular instance that we'll take a deeper dive, which is the Yosemite V3, and that's the state-of-the-art compute platform. And for them, like these are deployed at scale. So you have, for example, thousands and thousands of machines in racks and so on. So even if you can save like 1 or 2% energy costs or like get more capacity out of it, it translates to a huge dollar savings for them. So what they were interested in is see how can we deploy these self-awareness principles in a real setting which can work. And they sent like some of these nodes to us at UCI, where I'm a PhD student basically, and then we set it up in our small lab, and we have these nodes running. So ideally, I wanted to bring those one node here, but I couldn't. So I made a small video to kind of just see how would these things look like. You can see the designs, but it won't give you a feel online. So I'll play that video and then kind of show what I'm planning to solve the challenges there. So. All right, hello students. So here I am, and this is one hardware that I want to show you that represents how systems look like when you are talking about the cloud. So this piece of hardware is a loan from Facebook because we are working in collaboration with them on our research. This is one sled of the Yosemite V3 hardware, and as you can see, this has These are the parts which we will go over one by one. This is one sled which has 4 blades in them. So each of them are like one motherboard, but they're very compact. So first of all, how do you power this up? The sled goes in the chassis, and the chassis goes in the back of the rack. And the whole rack is powered by a bus bar. So normally there are 2 bars like this that powers the entire rack. But since we are in the lab setup right now, we are kind of using a small circuit to convert the DC bus bar power into standard ATX power supply, which is here. Okay. So normally you would not have this. Normally this would just slide into a data center rack, and then it will get power from there. So that's how it is normally powered in data centers. Now we have 2 fans here. These are the fans. Everything is modular, so you can live hot swap out things. So there are 2 fans. It gets pretty hot. So these are the 2 fans that keeps the motherboard cool down. Okay. So next, coming up here, so we have some more hardware. So first of all, this is the baseband controller board. So this is kind of the controller for the other motherboards that are there. So it's a very small microcontroller where you can send in commands remotely, and this will manage the rest of the hardware that's there. Next, we have a network interface card. So this is a 100 gigabits per second network interface card, which has 4 hosts connected to it. So the 4 hosts are the 4 blades. And it's again hot swappable, so you can pull it out if you want. Next, so let's pull this back. All right, so if we, so here, so these are each of the 4 motherboards. So let's bring one out, see what's inside. So this is one motherboard, and each sled has 4 of these. This is the CPU, there are 6 RAMs, and there's one PCIe SSD, and you have, this is M2, sorry, and you have a PCI slot if you want to add more stuff. So for example, if you have a GPU, you can add it here. These are very latest Intel processors, the ones which came out last year, and these are currently deployed in the data centers. All right, so let's now power one of this up and see what happens. It's really loud. And the way it's very modular. So if there are some disks, yeah, back again, right? All right, so that's kind of one system that we are playing around with. And the idea is, in order to make their lives easier, what they typically do is they do the worst case analysis, and which in some cases is no analysis, don't quote me. And they just configure everything like as if there's unlimited resource, right? So all the CPUs are running on performance governor, maximum turbo, and just wasting resources. So what the problem is, like, it's impossible for them to kind of look at every application, right? So look at which PyTorch neural network and configure, okay, this frequency should be 3.6 gigahertz, that one should be 2.2. It's not scalable. So what they want to do is see, okay, we have proposed all of this, like computational self-awareness. How do we actually deploy it in these machines, right? So if we can do it successfully, we'll have a second grant, but for now, it's the first one. So when in the design process, what the factors they kind of choose from is what are the applications that are running in general, whether they are storage applications, whether they're compute applications, a lot of database, memory, or so on. And they try to find a good mix of those workloads, and then also have some buffers for disaster recovery. And one particular knob which they are very interested in is turbo. So DVFS has been explored for a long time, where you have these fine-grained states. But to start with, at least to start from maximum performance, which is, for example, in this case, maybe 3 gigahertz, with turbo, it's one knob which kind of limits the frequency to the base frequency, right? And the idea is, if you know the memory patterns, so if you know that there are phases of compute and memory, and if you can figure out like what's the load like. So for example, these are 2 workloads. This is on top, we have the web, web is facebook.com, and this is, let's say, database, some internal database. And on the y-axis, we have the amount of power that's being consumed in both cases. And on the x-axis, this is 1 week's data, right? So power would correspond to the load. And you can see there are different types of load patterns, right? So for example, for web, you might expect in the evening, people are going back from work and they are probably more active on WhatsApp or Instagram. And so here you have more activity in certain parts of the day every day. But then let's say for a backup application, it might be that at 4 a.m. at night, when users are not that active, you would probably expect more activity. Right? So if we kind of figure out that these are the load patterns, and we also know which phases are compute phases, which phases are memory phases, and so on, then can we utilize that information to do a little more optimal configurations at runtime, right? So that's the idea. And to do that, our solution is using a little bit of self-awareness in there. So we have different policies. We have, for example, on the CPU, in this case, let's say 3 policies. You have task mapping, you have DVFS, and you have scheduling policies. So this is choosing which cores to map to which tasks, and this is choosing what's the frequency, and this is choosing when to preempt these tasks. And they might operate at entirely different scales of time. So some of them might be operating at milliseconds, some of them at microseconds, and so on. So you have these different types of policies that we need to kind of choose what these actions should be. Our initial prototype is called MARS. So it stands for Middleware for Adaptive Reflective Systems. And this is an open software release. So this is what we are trying to kind of use to solve this. So what exactly happens is Mars, when it's running on these systems, Linux-based systems, then it has different kinds of resource management policy models. And the managers can query these models. So for example, what will happen if I change an application from a small core to a big core? And then the model will, without running the application there, it will try to predict, okay, your performance may go up by 2 times, but your power will increase by 4 times. Right? That's an example. So across the stack, like I showed earlier, we have different sensors and we have different actuators. Right? So we take all these information together and we have different types of policies operating at different time intervals that are trying to choose what these actions should be, right? And so the key part of Mars is now adding these reflective system models. These models may correspond to, again, different layers of the stack, which the policies can use to make these decisions, right? So this is kind of the overall approach. So we still haven't been able to convince reviewers correctly. So my results are still not published yet, but hopefully when I'm here next time, I can show the results. But this is the approach that we are taking to kind of run on these machines. So what we are doing is we are making sure that we are aware of these power budgets at each layer. So there are, each machine on this rack has a budget. And then as you go up the hierarchy, you have kind of a hierarchical power budget. So we are trying to deploy Mars with an idea of what these budgets are and trying to see, like, for example, in the previous approximation case, we saw we had a QoS budget and then we were trying to configure the system. Here we are looking at these power budgets and then trying to configure some knobs within the existing system. Right? So that's the idea. So this is still ongoing research and some papers we are trying to publish. So we'll see where that goes. But so finally, any questions so far? Yeah. Please. Yes. Good question. Yeah. So I'll repeat the question. So I said, actually, I have a figure. Let me go back to that. There is a small figure here. I didn't go into the details, but what happens is there is a substation for each data center, and then there is a power path. So you have bigger, this is a main switching board, then there's a switching board, then there's a reactive power panel. So there is this hierarchy. And within that hierarchy, of course, as you go finer and finer, the budget decreases, right? And so what happens if you exceed that budget? So usually what happens is there is another small software daemon that's running on them And this is open source. Whatever I'm saying is all public information, right? So there is a paper called Dynamo. You can read it. So they have a distributed power capping protocol, which is constantly observing what the budgets are and what the current consumption is. And then whenever you try to exceed that budget, it will cap the system and all the systems below it. It's not a good solution, because if you cap, basically suddenly all the performance models will start failing, and they don't want that. Ideally, you don't want to cross those constraints, but it's better than tripping the circuit breakers, because if you don't have the daemon running and you cross that budget, it's gonna trip these entire row of racks, and that's not what we want, right? So initially, like when they started out, that was happening, and then they wrote that software to control it, and it's called Dynamo. It's an open CASSW'22 2014 or 15 paper, I think. Yeah. There's another nuance which I don't want to go too much into, but we can chat offline. Basically, the budgets are not equally distributed. So let's say you have a higher layer with 100 megawatts budget, and then in the lower layer, let's say you have 10 into 10, right? 10 megawatts. So it's not that the lower layer sum will equal to one layer higher. If you sum all the lower layers, it's slightly more than the layer above, and that is to account for local fluctuations. And because, let's say, the idea is here, all these machines are executing different types of load patterns, right? And the assumption is not all of them are going to peak together, right? If they all peak together, then that will fail, like whatever they're assuming. But if they all don't peak together, then they keep some margin in the worst case analysis. And so maybe the lower layers you're allocating slightly more, but if you end up using all the budget from the machines at the lower layer, then that is going to cause a problem in the higher layer. But right now, the way they do it is let it run, and if it fails, we'll cap it. It's not the best way, and hence we need these kind of more fine-grained optimizations. But yeah, that's to answer your question. Yeah. All right. Anything else? All right. So final part of my talk is about the application layer. So we are slightly going up. So we started architecture, then we looked at operating systems. Now we're going to application layer. And in that, I'll give you a quick overview of one or two of our papers. So we kind of identified a problem there's a big change in the industry where investors are pouring money into self-driving cars. And so we thought we'll write some papers on that to also get some research funding. So that's the background. So we kind of first developed a benchmark suite, which allows us to explore from a systems point of view what these self-driving pipeline might look like. So you have lots and lots of simulators, but the problem is most of them are looking at it from an application point of view. What we wanted is, if you have different systems, we want to explore different self-driving pipelines on it. So let's say Tesla is vouching for no radars or no LiDARs, but there are other companies like Waymo which are using radars. So we don't want to be tied down to one platform, and we want to explore different combinations of platforms. So for that, we were kind of with the focus of performance analysis in mind, we came up with this end-to-end self-driving pipeline benchmark suite. And this allows us to kind of usually follow a template where you have a sensing stage, a perception stage, planning stage, and actuation stage. And you have some smaller applications within each state, which represent more or less a real car, right? A self-driving car. So if you try to run it in an actual deployment, it may not work because not everything is kind of connected correctly, but it from a systems point of view, it will still exert the same pressure as you would expect to CPU, memories, and GPUs, right? So our purpose is to look at it from a systems point of view. So for that, we have this ESV 2021 paper, which kind of uses this end-to-end pipeline. And with that, what we do is, these texts are very small, but this is just looking at all the different kind of softwares that are running in the different layers of the stack for self-driving and different functions. And this is just showing that to analyze these small components, it's very hard, but Chauffeur will make our life easy. The title of the paper is Chauffeur. So instead of using full stack simulators, which requires extremely powerful GPUs if you're running Carla, Automare, for example, we try to run everything on a small NVIDIA board. And we want to make this easily deployable. So we have a very nice software using Dockers and stuff. So you just need to specify whether you're running on, let's say, TX2 or Drive PX2, and then it will compile the binaries accordingly with all the libraries linked correctly, and then you can just deploy this pipeline on these boards. Okay. So with that, I won't go too much into the details of the paper for time constraints, but the point is we use this to do a lot of research in terms of how does schedulability look like when you have different pipelines. So for example, these are the two boards primarily that we, on the paper we have described the characterizations on. So this is a Jetson TX2, Drive PX2. This has, Drive PX2 is actually representative of the state-of-the-art hardware. So this is what NVIDIA is proposing for self-driving cars. It has two SoCs which are a mirror of each other, runs real-time operating system. And this is a slightly simpler version of it. So for an example pipeline, we kind of analyze what the timings for each of these states are. And then we do a similar analysis for the second board, which is Drive PX2. And then we have some papers which kind of study the schedulability analysis for real-time operations using this benchmark. So we have some RTSS papers there. Then primarily I'm focused on memory. So I was looking into what these memory access patterns are. So all these applications are very periodic. So it takes one frame, processes it, proceeds to the next one. So you have these phasic behavior in the access pattern. So this is, for example, 3 applications from Chauffeur. This is lane detection, object detection, another lane detection. There's two of them. And then over time, this shows the main memory bandwidth, right? So this is a million transfers per second, main memory bandwidth. And you can see that there are these phases, right? Suddenly there are some spikes. And so if you have this kind of a memory phasic pattern, and these are predictable patterns, then can we use some kind of, in a hypothetical scenario where you don't have enough memory, can we use this information to improve the performance? So we are assuming that there is some memory contention, and this is a hypothetical scenario where instead of, let's say, 1 gigabytes or what have you, I'm restricting it to 512 megabytes. In that case, we can show that we can actually proactively identify the memory pages that we can swap out earlier. So if you have 512 megabytes, then you can't fit the entire pipeline in memory, right? You have to kind of use the storage system as the backup in the memory hierarchy. So if all the pages do not fit in the main memory, then I can identify some good pages to swap out ahead of time, and then use this periodic behavior to improve the performance of the pipeline. So we developed this another solution called ProSwap, which we just published in NAS 2022. And so we compare it with like the default on-demand governor. And using eBPF, we have these predictions going on. And we can also adapt like what's the frequency of monitoring. Should it be 1 second? Should it be 5 seconds? And so on. So it's a very recent paper. I think it's not out yet, but it should be coming out soon in the proceedings. Yeah, so we have 5 minutes to wrap up. So I think I have like given you an overview of the different layers of the abstraction and memory that I'm looking at. So overall, my goal is to kind of look at this memory manager that's sitting here and these different memory layers of abstraction, and have these different kind of aspects of self-awareness which we can prototype on these memory layers of the stack. So those we are not there yet in terms of achieving a full computational self-aware system, but we are trying like one step at a time, right? So earlier there was no goal awareness, there was no approximation, but we are trying to make like baby steps in that direction. So there are not just there's a lot of research that's going on. Even in my research group, there are other PhD students who are working on different aspects of self-awareness. For example, if you can understand that your system is kind of going through a tough phase and it's going to fail soon, can you start healing the system automatically? So that's one area of research, for example. And then ideally, we would want all aspects of self-awareness in one complete manager, which doesn't have a lot of overhead, but we are not there yet, right? So that's kind of the general trend that we are trying to work towards. And overall, particularly, I'm focused on realizing these principles for an end-to-end solution, both like vertically and laterally. So we want these solutions to work across all the applications that are running on the system, and also so that these can be deployed at scale in real settings, right? So those are kind of the three takeaways that I had. Let's see, I think with this, yeah, there are some. My advisor is also working on some other projects, which no, I am not a part of, but there are some other research activities with computational self-awareness that he's doing, and you can visit our website to know more about them. Yeah, these are some publications at different layers. Yeah, with that, I'd like to conclude the talk. Again, like a very many thank you to, first of all, Professor Daniel for inviting me, and all the organizers of CAS for giving me the opportunity to present my research. So I really appreciate that. I'm grateful for that. And then I'd like to open it up for questions. This is my advisor, by the way, and I am here in this picture. You can see. Yeah. All right. Thank you.
So thank you, Deep. Do we have any questions?
Yes.
Mateus.
Actually, I have a lot of questions, but I don't want to
Sure.
monopolize the session.
Yeah.
I guess my question is still regarding that other question that I made before.
Yeah.
I see that you have cross-layer, self-awareness and budgeting and stuff.
Yes.
Okay, but and also that you want to apply it in horizontally and vertically.
Yeah.
So, like, do you already consider situations where a particular part of the system cannot be approximated in any way, while other can more freely be approximated, and then the budgets from this side cannot be actually met, so you can compensate other parts of the system eventually. Does that happen right now, or are you planning on adding this type of feature as well?
Very good point. So I'll start with first an easy answer. Is just specific to approximation that already happens, because, for example, there are certain segments in the memory where we cannot approximate, right? So that's already kind of considered in when we deploy schemes, because operating system is critical, and even within these applications there are some critical areas which we don't touch. But what you are asking is, like, there can be some pages which are now critical but later on may become non-critical, right? So that's in the broader sense. In my work, I haven't touched that yet, especially for approximation. But for power budgets, we are actually doing that. So I didn't show the results yet, but we are considering, like, there might be some racks where when these peaks are happening, that you might want to direct more budget there. Right now, it's not done. It's just flat budgeting. But yeah, of course, that's a very good idea, and we want to exploit that. So I don't have the working solution yet, but we are trying to do that for the power budget case.
Any other question? I mean, I had the opportunity to discuss this kind of things in Pelotas with Deep, so
Yeah.
my questions are kind of covered, let's say. 7 questions? Okay.
Yeah.
I have a second one. I may have 7 questions, but not right now.
We can also, like, in the evening, I don't know what the plans are, but usually self-awareness requires some beer, so we grab all beer.
Oh, that's a great idea.
Yeah.
Yeah, that's a great idea. My second question is, do you guys plan on trying other types of policy update strategies? Because that table doesn't seem to scale very well as we increase more options for and more states. It's the same problem of reinforcement learning.
Absolutely, and you are right. So the table that I don't want to go. Basically, the thing is, the table that I have right now, yes, for 3 layers it works, and for 3 layers it's already 700 states. I tried 4 layers, it wasn't good, so I omitted it from the paper. there is a problem of convergence as you scale it up. So just for Q learning, I think the way I have it here, it's not going to work. My idea is for that we definitely need some distributed learning to kind of, maybe there are certain lower learning elements which are looking at maybe one layer of the hierarchy, and then you have an overall coordinator. So it's a hierarchical some form of learning, but it may not necessarily be Q learning actually. So for example, when we were looking at these one layers, I did not present that part, but let me show you quickly. Actually, I don't have the slides, but here we had this other paper, which was this one, the self-adaptive memory approximation. So there we are actually using just formal control theory for one layer. So we do a system identification of, we take first L1, then just L2 without any coordination. And then we are using system identification to develop the PI controller, and the PI controller looks into just one application QoS and tries to tune it. So the idea is, yeah, it's not like Q learning or TD lambda fits every solution. And for example, in the self-healing one, we are developing completely new things. So for example, this is not my research, my colleagues are doing it. So in the processor, they have added a trace abstraction layer. So you have these instruction traces that are coming in, and the trace abstraction layer is kind of filtering out the most relevant information. And with that, they have some small circuit within the hardware to understand when like things are going wrong within the processor. So these are some hardware architecture, like new architectures, which they're primarily focusing on parts of this problem. For them, it's basically runtime verification and kind of healing when things go wrong. For my case, yeah, I chose TD lambda because it was a good solution for this problem. But there are like numerous approaches, and there are books on what kind of approaches you can take. There is also meta learning, where your system is aware that there is a model of the system, and then that awareness kind of evolves over time. So there are like lots of research, but it's very infant, I think. There needs to be a lot of work here. We are taking the first baby steps. But yeah, again, like as long as you have some way to understand the systems and the environment, and also use that information for these reflection, I think that's the way to go. Now, whether that's Q learning, whether that's regression models, control theory, that's up for debate.
Hi, good afternoon. Great presentation. I have one pre-question, which is, do you plan on integrating the layers?
That's a good question. Not for my thesis, because I can't graduate. I'm already in my 6th year. I want to finish with the last power stuff I'm doing right now, but that definitely comes up a lot. So I don't know whether I will pursue it, but I think identifying, at least if we can't do from architecture or device, because it's not possible for me to actually change a lot of stuff across the stack, at least starting from the operating systems layer, CUDA library and application, I think there's definitely opportunities. Even if we just take operating systems layer, I think there are still a lot of knobs to kind of look into. So far, I've only looked into memory and compute, haven't even touched IO. Then there's network, and then that's just OS. Then you go to CUDA, and you go OpenCV, and then you go further up. So there is a lot of opportunity there, but I don't think I will be doing it in my PhD thesis, at least.
Yeah, my question would be, what would be your plan? Because usually one option would be to choose a layer, let's say circuit layer, and do all the optimization, like some coarse grain optimization on the circuit layer, and then use it as a benchmark for the next layer, and so on and so on. I mean, to do something really good would be like a lot of work, but maybe just to get some corner cases, you could just like start choosing a layer and see what happens. Maybe that can be done with not so much work, but of course doing it like optimally, then two PhD theses more.
Maybe more, if I can become a professor, maybe I'll hire some students to
Deeps group then.
Okay,
thank you.
Thank you.
Any other question? Mateus? Okay, so let's thank Biswadip, right?
Thank you.
For the talk.